Okay, so now we'll talk about another tool which is used to analyze controllers in the frequency domain, which is the Nyquist plot or the polar plot. Okay, it's strongly related to the Bode plot, but we will see what is the difference here. Okay, the difference is that, okay, we have the real axis and the imaginary axis, and the idea here is to plot the magnitude and phase on the same plot. So whatever frequency you are talking about, let's say at certain omega p, for example, so we are expressing both magnitude and phase at the same time. So this is, for example, is the magnitude and this is the phase. Okay, so you always at any point here you always have the magnitude and the phase. Okay, so let's say, for example, you start here at omega equals to 0. Let's say that lower frequencies have higher magnitudes, and then they start to have lower and lower magnitudes as they go towards, for example, infinity. So for every point, okay, you plot the magnitude and phase on top of each other. Okay, so you always have the magnitude and the phase together on the same figure. Okay, if we do it like this, it's called the polar plot or the Nyquist plot. And from this plot, okay, it's important to know that if you're plotting, of course we are talking about the open loop system also. So let's say that the open loop transfer function is actually, or the open loop frequency response is gc of omega times g of omega. Okay, so this is the combined open loop, okay, which is then being used in a closed loop system. But for now we'll focus on the open loop. We know that from our previous studies is that we always had in the denominator, okay, we had this term which is 1 plus gc of omega times g of omega 1 plus the open loop, okay, and that's why we always wanted to avoid this -1. So we want to avoid that the open loop goes to -1. And when we talk about the Bode plots, we were mostly talking about magnitude and phase. So magnitude equals 1, which is 0 dB, and phase equals to minus 180 degrees. Okay, but here the objective is to try to stay away from this -1 point. So how can we calculate the gain and phase margin from this plot? Okay, so the gain margin is simply, so how can, when we increase the gain, what we do is we essentially bring this whole figure like towards this direction. So the question then becomes, how much gain can I apply to the system before I hit this -1 point? And the same thing for the phase margin. So since the positive phase is measured like this, so the phase margin is basically how much phase you can apply, or how much rotation you can apply in this clockwise direction, okay, in order before it hits the -1. So how much rotation you apply before you hit -1, and how much magnitude you apply before you hit the -1, and these two define the gain margin and phase margin. Okay, it's not as intuitive as the Bode plot, it's clear, but or maybe not easy to calculate as the Bode plot. But there is another advantage here. Let's say, let's take another example. Okay, and let's say that you have your polar plot or your Nyquist plot is something, okay, maybe this doesn't look very nice here. Okay, let's draw this again. Okay, so let's say that you have a situation like this. Okay, okay, and the -1 point is, let's say, here. Okay, so what information can we extract from this? If we look at the, let's call this omega A, for example, and let's call this omega B, let's say. So although you clearly have a very good gain margin, okay, so you need to multiply by a very huge number in order to reach this -1, maybe even infinity, and also in order for this to rotate, it hits the -1, it has a good phase margin. But if you look at this one here, if it rotates by some value and then is multiplied by some value, it will hit the -1. So a combination, okay, so the point is here is that you can have a combination, okay, of both gain and phase uncertainties in your system, okay? So this combination of gain and phase uncertainties can be examined in a better way from the Nyquist plot. So in this case, if you have some rotation and some gain, you will eventually hit the -1. Although the gain margin and phase margin as is are quite good, but your system is not robust as such. So the Nyquist plot can give you a measurement for how robust your system is. So it can give you more indication of your system robustness. Okay, so because since we are designing gain and phase margin based on the uncertainties, we can never know exactly whether we really have whether they can happen together or not. So we're not sure. Maybe there can be a combination of gain and phase that can happen to the system. There can be some delay that is unexpected delay and unexpected gain that can happen together and lead to this terrible -1 point, which is leading to instability. And this can be easily extracted in a much better way from the Nyquist plot. Okay, so this is how you understand the problem, or can extract the problem. But what about solving the problem? How can you solve this? Well, one way is, okay, so we say omega b is a problem for me. Okay, so why not design a band stop filter or a band stop or notch filter that, say, for example, passes all the frequencies and has some band stop here. So when you try to stop this band, okay, what you're doing effectively is that you are pulling this backwards like this. And when you do that, you avoid this kind of problem. So you make your system more robust. So by doing this, you can make your system more robust. Therefore, you can actually examine your system and see where your problematic frequencies are and try to design a filter that is trying to handle this. And this is actually very interesting because you can use all the beautiful tools for filter design, okay? And in order to design a robust controller or robust system, robust feedback control system, this is actually sounds very beautiful, that you can use the filter design theory in order to increase the robustness of your controller. So it sounds nice. And even nicer when we go to the digital control, that if you want to design a robust digital control system, so then you will be doing digital filter design, which is even nicer. Okay, and this shows that actually there is kind of a strong relationship between signals and systems, control theory, and digital signal processing in general. And it's very important. It's very important to understand all these basics, and it's very important to use the useful tools and useful theory that you learn from different subjects and different topics and apply them in different fields. So